So this is from the TU München, and we're talking about the Cubo maker, as I see, right? Yeah. So converting some path problem to a Cubo and then compile it into the quantum computer, so to speak, right? Okay. So then the stage is all yours, and thank you very much for being here.
No? Okay, all right. So yeah, thanks for having me. My name is Damian. I'm from the Technical University of Munich, from the Chair for Design Automation. And today I would like to talk to you about how we plan to support end users in realizing quantum computing applications. And in that, we want to look at some problems that we have found that many end users occur, and our solutions that we have provided for these problems. So many of you might be familiar with the general process of how to solve some problem using quantum computing. Typically, you start with a problem, you find some algorithm that might be suitable for the problem, and then you encode the problem into some format that the algorithm can work with, and you translate all of this into a quantum circuit. The quantum circuit, you run it on some device, for instance, and you end up with a histogram. And this histogram you decode to get your actual solutions. Now, for people who are already into the field of quantum computing, this sounds like a very simple task. But actually, if you're someone coming from the outside, then there's a lot of places where things can go wrong or where things can become more difficult. Actually, already in the very first step of encoding, there are areas that require quite a lot of expertise in quantum computing. For instance, what does it even mean to find an algorithm that is suitable for my problem? I would need to know how the algorithms work, which algorithm works best for me, and so on. And then how do I translate this problem into a format that the algorithm can work with? And even if we can answer these questions, there's further problems, like during execution, where we have to work with compilation, and you have the questions of how do we actually want to compile our problem? And we have to think about physical considerations, like what devices are actually best used for our specific problem. So all in all, it's very clear that there are many places where end users can face problems. This is especially the case when people are not really experts in quantum computing. And as quantum computing becomes more and more popular, many people from the outside are coming in. And they definitely need something like tool support. They need software that can help them in the field of quantum computing. And for that, we have come up with the Munich Quantum Toolkit, the MQT, which is just a selection of open source Python software and also C++ software that users can employ to solve different problems all around the quantum computing stack. In fact, for us, that includes the application layer, but it also includes layers such as simulation, compilation, verification, error correction, even some hardware design. And we have some common data structures in the background that you can use to actually represent your quantum states and stuff like that. But in this presentation, we're going to look just at the application layer, which is the layer that most end users are actually going to interact with. Now, going back to this workflow diagram, as mentioned earlier, there are a lot of steps that can be quite difficult here. But also, there are areas that are quite error-prone. Imagine if you're working on a very big algorithm, then it can happen really fast that some mistake happens somewhere inside the circuit. And once you have a big circuit, it's very, very difficult to actually find this error. So one would think, wouldn't it be nice to have some sort of framework that goes around all of this workflow, that giving some problem formulation and some quantum algorithm automatically does all the encoding and running for us, and we just need to call this framework. Well, we're trying to come up with something like this. And for that, we have split the workflow into two domains, the classical domain and the quantum domain. In the classical domain, the end user selects some problem specification and some algorithm, and then the tool automatically transforms this into a quantum circuit, runs the circuit, decodes the results, and finally translates the results back into the classical domain. And there the end user can access them again. The long-term vision for this is to support a very large variety of different problem classes. And we also want to provide the same interface that end users might already know from existing classical solvers. And a very cool thing about this idea is that the end user is completely shielded from all required quantum computing knowledge, because everything related to quantum happens in the backend. They do not need to interact with it at all. And this tool is what we call the MQT problem solver, and it's available on GitHub. And as a starting implementation, we support just a few different problem specifications, but we are working on actually improving this further. Now, going back to this workflow diagram, looking more specifically at the execution and decoding part. Nowadays, there's really two ways that one can actually run a quantum circuit. Either you use some existing quantum device for it, or you simulate it. But in both cases, we face a similar problem. If we want to run some algorithm that requires, let's say, 2,000 qubits, then this is not going to work, because neither quantum devices nor simulators provide so many qubits. That's why nowadays an alternative approach is becoming popular that's called resource estimation. In resource estimation, we don't actually run the circuit, but instead we get some estimate on required numbers of qubits and required runtime and so on. Now this way we do not get the actual results of the circuit, but we get some sort of estimate on what we can expect from the circuit. Like when can we actually expect the circuit to be executable on real hardware by comparing it with vendor roadmaps. Going back once again to this workflow, there's more specific areas that actually could also help with, could also require some help for end users. For instance, the encoding part. Now, if we have some problem and some quantum algorithm, and we want to create a quantum circuit for this, this can be hard or difficult, but also easy, depending on what exact problem you're looking at. Let's say, for instance, we're looking at a max-cut problem. We already have a lot of literature on how to create quantum circuits for max-cut problems, so we will definitely be able to somehow create a circuit for this. On the other hand, like what if we look at a traveling salesperson problem? Once again, there's existing literature, there's existing tools. It's not going to be such a big problem to create circuits for these. But what happens if we look at something just slightly more complex? Maybe the same max-cut or traveling salesperson problem with some additional constraints. Well, it happens very fast that the simple process can become a very big question mark. And the big problem here is that actually if you're some end user coming from the industry, then usually you don't have to look at some pure max-cut or some pure traveling salesperson problem, but you have your very specific constraints, and you somehow need to create a quantum algorithm for this. And for that, we have created MQT Cubo Maker. And let's look at this with an example. Here we have a circuit, and let's imagine we're some logistics company that needs to deliver objects to different locations, marked by these vertices from 1 to 10. Now, we have some specific constraints. For instance, we want to visit vertices 1 to 8 exactly once, but 9 and 10, we want to visit them twice. Maybe because 9 and 10 have some locations that need multiple deliveries a day. Also, we don't want to visit vertex 2 before vertex 3. Maybe we need to pick up something from location 3 and bring to location 2. Also, we don't want to take the edge from vertex 5 to vertex 6. Maybe we know that there's construction work going on that street, so we don't want to risk getting into a traffic jam. And also, we want to enter the starting vertex so that we can leave the car there overnight, for instance. Now, there are existing quantum algorithms for this. For instance, the quantum approximate optimization algorithm, QAOA. And the thing is that these algorithms usually require some sort of format. In the case of QAOA, this is the Kuber formulation. But the problem is, it's not quite easy to create a Kuber formulation for some problem instance if it's complex like this. In fact, if you have never used quantum computing before, then most likely this is going to be almost impossible for you. And if you have experience with quantum computing, even then it's going to take a very, very long time. And you end up with like a big formula and have no way of knowing, maybe I've made a mistake somewhere in the middle there. And for that, we use MQT Cubo Maker now. And once again, it's open source and available on GitHub. And it's a tool that can create Cubo formulations for some specific problems instances. In particular, it can create a Cubo formulations for all sorts of pathfinding problems in directed graphs, as long as they can be translated into a set of constraints like these here. And for that, we also have a graphical user interface so that you can actually use it without writing any code at all, where you can just select the constraints that you're interested in. And then, by clicking just a single button, you can generate a Cubo formulation. And another cool thing about this is that you can also change encodings. So typically, Cubo formulations are given in some sort of encoding, such as one-hot encoding or binary encoding. And if you want to change your encoding, then you have to start all over from scratch if you're doing all of this manually. Now with this tool, you just press a single button and change from one-hot to binary, and you get the new cubo formulation immediately. Now, what does it mean to get a cubo formulation? Well, the MQT cubo maker supports multiple different output formats. We have a cubo matrix, but we also support a cubo cost function that might be a bit easier to read. And we also support generating directly a quantum circuit for your problem. This way, if you have no experience with quantum computing at all, you get the circuit immediately, and you're once again effectively shielded from everything that requires quantum knowledge. Now, returning once again to the workflow, there's another area where end users might need support, and that's in executing a quantum circuit. Yeah, so that's in executing a quantum circuit. Typically, you can't just run a quantum circuit, you need to compile it first. And that begs the question, how can we actually optimally compile a quantum circuit? That's actually a quite difficult question that many have looked at. But in our case, we split this task into two individual steps. The first step is device selection. Let's imagine we have a set of different quantum computing devices, and we want to select which device is actually the best one for our specific circuit. The second then once we have the quantum device, the second step is the actual compilation. Each device supports a set of native gates that we need to translate our circuit to, and then we also need to map our circuit to the topology of this device. Now, putting these things together, we get a tool that we call the MQT predictor. The MQT predictor is an automated tool that does the device selection and compilation for us based on different machine learning models. For device selection, we use a classifier that decides the optimal device based on some characteristics of the circuit, such as the gates that we want to use and similar things. For compilation, we use a reinforcement learning model. In this reinforcement learning model, we train it using a large set of different circuits for different quantum devices using some figure of merit. In our case, we use as a figure of merit the expected fidelity. And after training, we end up with a reinforcement learning model that can compile for this specific device a large number of different circuits. And putting these things together, we end up with MQT predictor. It's an easy-to-use tool. Once again, it's a black box model. You do not need any quantum computing expertise to run it. And another cool thing is that the figure of merit that you can use is customizable. So if we ever decide that maybe the expected fidelity is not really what we want to look at, then we can easily change it. Now, one thing I've talked a lot about is using different software to help end users. But any software can only ever be as good as the tests we run it on. That's why we've also come up with MQT Bench. MQT Bench is a benchmark suite that contains more than 70,000 different quantum circuits on different abstraction levels that one can use to test their software. So you can imagine if we, for instance, write two different compilers, we can use the circuits in this benchmark suite to compare them and evaluate them. MQT Bench is available as an online tool. We have a web interface where you can actually select the circuits that you are interested in, the types of algorithms you're interested in, and also the abstraction level you want. Maybe you want the circuits already compiled to a very specific device. Maybe you want them compiled or just translated to a set of native gates. And yeah, with that, we've come to the end. Once again, to repeat it quickly, it's a very important goal for us to support end users by providing different tools. Tools like Problem Solver to hide the entire quantum workflow, tools like the Cubo Maker that can help with very specific problems, and tools like the Predictor that can handle the circuit compilation for you. But there's also many areas that still need further support. And for this, we provide tools such as MQT Bench to actually test any software you want to write. Now, as quantum computing becomes better and better, as I mentioned earlier, for sure there will be people coming in from the outside. And we are running the risk that at one point, the quantum hardware might be really good, but the tools we have is not good enough at all. And that's why I think it should be our main goal to make quantum computing accessible to all using tools like these. Thanks a lot, and I'm open to any questions.
Indeed, thank you very much. Here goes our first question and the second one.
Thank you for the presentation and the work you do at TUM. So I have actually two short questions. The first one, am I understanding correctly, like there's no code snippets that you could provide because it's like an online interface for the user to just click and drag and solve the problems? And the second question is, it came into my mind because recently a colleague from a different group at Focus published a Kubo solver benchmark where he also uses the minisync approach. And how is your Kubo problem solver maker different from like the minisync approach is also kind of a staple in the Kubo industry? Thank you.
Good questions. The thing about the Kubo maker is that it's not actually meant to be a solver. It's meant to be a tool that helps you actually create the formulations of the problems. So also this online tool that I showed you before, it doesn't give you the exact results of the Kubo question. It just gives you the Kubo formulation. So because of that, you still need to use some code later on if you actually want to solve it, or you use one of the other tools that I've talked about to actually input it there. But yeah, it doesn't give you the exact results, so you do still need some sort of computation. And I think the same question also replies to the other question, since yeah, we do not really do the solving.
I have a question about the resource estimation.
Yes, of course.
As a user, can your tool help me understand how big of a problem instance I need before quantum computing will be faster than classical computing?
Admittedly, the resource estimation part is still like pretty much work in progress. I do not think that we have some sort of estimation like this, but I think this is actually something that's definitely on our roadmap, because it seems like it's a quite reasonable goal and it shouldn't be too hard to implement, but currently cannot do that.
Yes, first of all, let me answer your question. There has been 2 papers on that, one from Microsoft and one from Google, and they basically estimate, after crunching all the numbers like magic state distillation, everything, that if you've a quadratic speed up, you need a problem that runs at least for 2 weeks. So quadratic is most likely not where it's at. They say quartic is more realistic. And yes, now my question for the Kubo maker, and how do you handle the constraints? Like, you need to have this penalty factors, which can turn out quite of a mess if you automate their determination, because like if you do them too big, then the quantum computer can't resolve the actual problem anymore. If you do them too small, then the constraints might be violated. How do you solve that?
Yeah, going back to the slide. Yeah, so here you see like a set of different constraints that we support. For all of these constraints, we have pre-computed how they interact with each other. So that means we have some general penalty factors for these sorts of interactions that we already have, that we already know. So the Kubo maker just uses them. So none of these constraints interact in a way that's so complex that we cannot use these pre-computed constraints. But also, admittedly, we haven't done any evaluation on how well these specific constraints perform exactly. So, sorry, these specific penalty factors perform. So that means that we could still do some sort of testing to see if the penalty factors that we're using actually work well, specifically with existing quantum devices. But yeah, currently all of these are pre-computed.
Okay, so I would suggest that we set up the next talk, and if there is one more in the meantime, so who's the next one? Data flow based optimization? No? Not today? Oh, it's online? Oh, that is interesting. Okay, good. Then it's already almost set up, right? So one more question maybe, or is everything fine so far? Okay, then let's thank you, Damian, again. Yeah.